And we're rolling. Excellent. All right, this is the Harmonic series, and my name is Jacob McClinton. Let's get started. So, starting with the basics, sound is our perception of an oscillation, a series of compressions and rarefactions in the air that we can model as a wave. Like any wave, sound can have amplitude, which impacts its volume, and frequency, which we perceive as pitch, which will become really important in understanding the harmonic series. The harmonic series describes a phenomenon in acoustics where, when a pure tone is performed, a sequence of frequencies above that tone, corresponding to integer multiples of its frequency, will also be audible. Simply put, when a note is played, not just that pitch is being produced. A note with twice the frequency, called an overtone, will also be produced. So will a note with 3 times the frequency, and 4 times, and 5 times, and 6 times, and so on, etc., basically infinitely out. So the easiest way to picture this is going to be a string. When you pluck a string, it's going to vibrate. It's going to vibrate along its entire length back and forth. But there's also going to be nodes that are produced. And the nodes are going to appear at even intervals along the string. So here's an example of one vibration, 0 nodes. And then here would be example of 1 node, which is going to create 2 waves. 3 nodes right here, 3 waves. This is essentially what the harmonic series is describing. So the existence of overtones is extremely important and consequential. The relative amplitudes of each consecutive harmonic are what create our perception of timbre, also known as sound quality. For example, a flute and a violin both playing the same note, in this case concert A equal to 440 Hz, sound different, despite presumably creating the same sound. Remember, a sound wave only has amplitude and frequency, so why do they sound different? So obviously the answer is because of the harmonic series. Both instruments are producing the same fundamental frequency, in this case concert A, but the relative volumes of their overtones are way, way different. The flute is producing a pure tone at an overwhelming volume compared to all of its other overtones. Essentially, what you're hearing when you hear a flute is a pure sine wave at whatever frequency is the note being played. That aspect is what's giving the flute such a pure resonant sound. On the other hand, the violin is basically playing a cacophony of overtones. You can see it here, it's all over the map. And that quality is going to So this brings us to the next point. The only note in the harmonic series with overtones is the fundamental frequency. For example, the first overtone, also equal to the second harmonic, would not produce its own overtones in tandem to the fundamental frequency. It just is not possible. So that leads us to a pretty interesting conclusion. Every timbre that you could think of has to be accessible with a certain dynamic makeup of overtones. So that means any pitch sound can be created with an infinite series of sine waves. And that's kind of what the graph displayed on the screen is telling us. We have a fundamental frequency of 100, followed by the second overtone, 300, as well as the fourth overtone, 500. And the resultant wave is displayed on the right. And depending on how strong the amplitude is on the overtones, you can create a whole bunch of different sounding timbres with just these 3 waves. So this is very basically actually the concept behind every synthesizer. The only exceptions to this rule are non-pitch sounds called inharmonicity. These can include percussive instruments, for example cymbal crashes, where the frequencies being created are fully dissonant and no pitch is perceived, as well as asymmetric instruments like church bells, which produce non-integer overtones, but that's a whole other can of worms. So there's another extremely important musical application of the harmonic series in that it fully describes consonants. For example, the ratio of the first overtone to the fundamental frequency is 2 to 1. For concert A4, the first overtone would be 880 hertz. This interval is called the octave, and it's the most consonant that any note can be to another note, exactly twice the frequency. In fact, it's so consonant that we actually just perceive it as being the same note again, just higher. And as such, we call it A again. From here, we go from twice the fundamental frequency to 3 times the fundamental frequency for a ratio of 3 to 2. This interval is the perfect fifth, and it's the second most consonant that any note can be to any other note, exactly 1.5 times the frequency. The next interval, 4 to 3, is the perfect fourth and is the third most consonant, and the next interval, 5 to 4, is the major third, and it's the fourth most consonant. In fact, the first 5 harmonics on the harmonic series line up with the major chord, which means that humans have intuitively known about the power of this series for millennia. A deep, rich sound.